Can you see my screen?
Yes.
Yes, we can now.
So yesterday we were facing problems with gravity loading. So actually there is an issue. The issue is that if you have defined inertia, it's in Abaqus documentation. So I defined in inertia point mass inertia. So we cannot do that. So for this, for applying gravity, we have to apply gravity for the whole model. We cannot apply gravity to individual point masses. So that was the reason we're not able to we're not able to yes, I'm not sure what time step had we defined here. 3. So let's see what happens. Probably it will. Okay, let's see now. So here I'll maybe delete this. Okay, and the gravity, right, on whole model. Let's just find this is in step 1. You can move it to left from initial interaction. What is the interaction? This interaction property 1. So maybe it was, I think, yes. So let's submit this and see what happens. And I hope I have all filled out. Yes, it's fine. Could have asked for acceleration as well. And I will also request for acceleration. And in step maybe I hope this is taken care of. No, 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 no. It is not taken care of. 500. Sorry. We need to kill this again. So right, if I kill it right now, it will kind of hang. So it's better when it starts Abacus explicit and writes the output in initial frame, then kill it. Yes, now we can kill it. Submit it again and wait for a few minutes to complete it. It is moving now. So see what happens. It's fixed everything. I applied gravity instantaneously, so there is some dynamics here. So see this. Finally, it stabilizes. See, it stabilizes, tends to stabilize because most is now zero and there is some. So it is about to crush or whatever. Let's see what has happened. So very soon it will come to rest at the top and then again strike it. This will approximately take 10 minutes to complete, I think, because approximately 200 for one, so 600 for three. You can also model the steel and see if there is any plastic strain or anything. Does it cause damage to steel also or not? Not damage really, but plastic strain or anything. I think it must have collided again. Maybe. Yes. Just see what happens. It hits this and it gets, see how it falls down. So now it will see what will happen to it. It will fall down from here. Okay. Yes. Now, honestly, why did it fall down after the second collision? The first it hit somewhere here. Second it hit there, right? In second collision, it didn't hit. See, it was not perfect, right? Perfect in the sense the bottom surface of the wall didn't collide with the bottom surface of the this load or whatever drop this cube. It didn't collide perfectly with the concrete element. So due to this, obviously rotation was imparted. Why? See, sorry, here. Uh, these two edges have not collided, the opposite edges have. So load is applied on them. That will cause rotation. Now it collides like this. See? There's no need to run it again because it has fallen. Okay. Now you'll say, why did this happen? It collided here. Okay. So it didn't, when it collided, it didn't get equal reaction on the whole surface. So small rotation was imparted to it. Okay. Then while it went up and came back, due to gravity, it had good rotation imparted and then fall. So I think I can kill the job. There is no need further. So do you have any questions? Anything? No.
No.
Then I'll save this and I'll rest of the models you can correct yourself. Just select hold model. You can't define it individually for a point mass. So I'll just, I'm not sure if I've done this, but yes. Hmm. Yes. So now so we'll start another project. This is very small, not very. So what the problem is, we'll model a cantilever beam under pressure. Okay. You will use Abaqus standard, and these are the material properties, linear elastic analysis. Okay. But I will model it using solid, shell, and beam element. And you have to firstly, can you calculate the displacement at the tip, displacement here, if this load configuration is given? Anyone? Convert this into line load and then use the formula WL raised to 4 by 8 something like that. You should calculate the tip displacement, and you should be able to do it. It's taught in maybe second year of civil engineering, so it's not a big deal. Two, no. So first module, I'll name it as solid elements. Okay. What is the section? Let's do the same unit which I have been using. 2550. Like this. I'll do it quickly. Because solid we have model n of solid, right? 0, 0. It's 2000. Yes. Go to property. Density is 7.8 E. Mhm. So 2E5, 0.3. It's actually steel. Material is steel. Static general. Keep it maybe this no doesn't matter. This is elastic analysis, so no need to do anything with this. The idea is I want to show you the difference between shell and other elements. Field output. This is fine. Okay. Let's keep it as it is. Following that, no interaction load. Boundary condition. Create. Maybe here. Take this edge. Okay. What about load? Pressure. This is the pressure, right? It is in first step. Following that, we'll go to mesh and not 100, obviously. I think let's start with 20. First analysis, let's do 20. And I know the converge mesh. So let's do like this. Okay. Okay, now the issue is if I ask you and you don't do it. Okay. Yes. So let mesh continue to this. I'll now go here 10. Okay. 5.39, right? The converged mesh is this 6.25. Okay. It is. You have to do the mesh convergence study. Okay. This is not very difficult. Neither will you get any errors because it is linear analysis. We'll do one more 5. Sorry, like this 5. The good thing is it doesn't take a lot of time. See. For 20, we got 5.3 something. Let's see what we get for 10. 4.99. Okay. Is this you? Sorry, you 4.87. So if I go like this, it's 4.87, which is good. Okay, which is good. See, finally. What is this? 4.84. So the mesh converts at 6.25 because 4.87, 4.84. What is the difference? It's very small, right? So the converged mesh is 6.25 millimeter. You should document this, or if you want. Okay. Can anyone guess the analytical solution from this? What value will you get analytically? Anyone?
I think I got 192.
No, no, it will be 4.8 millimeter.
Uh,
Probably you have done the mistake, some mistake. Anyways, so this is simple, nothing great about it, right? But let's go a little bit. So, do you know Euler-Bernoulli beam theory? Anyone? Okay. Firstly, I will never discuss that. If you want to study it, study from any book you want. But just have you seen this equation ever? Anyone?
deflection.
Yes, for deflection, this is the differential equation of a beam under some load. General differential equation. Anyways, Study Euler-Bernoulli beam theory. So beam element in Abaqus uses Euler-Bernoulli beam theory. So I'll create a new module beam element. So the idea is to show you how to model with beam and shell elements. Okay. Now click OK. Here I'll select 3D, but I'll go with wire. Okay, wire element, because beam element is like a line. Okay, and select maybe something like this and give it a dimension. How much? 2000, right? 2000 millimeter. So then you click this, hit this, and this is your beam element. Beam. Okay. But obviously we have to define these things. Okay. Now I'll show you there is something called profile. So you have to know where is it. You have to define this profile for beam element. I'll show you. See, when you define a section, you go for beam. Okay, go for beam. Then it says, what do you want? Material is already given, but profile name. So I have to create a profile. Profile is like a rectangular. You can say rectangular or box, maybe whatever you want. Not really box, rectangular. Okay, like this. So what is your B? It is 50 millimeter. And what is your A? It is 25 millimeter. See, 25, 50, right? This is your profile. So you have to give this profile, and we are, oh my God. Okay. Profile one, I have to do something called this. Okay. Okay. Then assign the section. Following that assembly, bring it here. Following that step, initial, static, general, keep everything as it is. No need to worry. Field output is already created, I guess. Well, there are a lot of no, I don't need too much. I just need displacement. I can even skip stress. Following that, no interaction, go to load, create displacement rotation, constraint everything. Okay, so this is fixed. Load. Which load should we apply? Line load. Where? Here. How much? Okay. Along Y. Can you tell me how much should we apply? Line load. Anyone?
What is the question?
Line load. How much should we apply? How much line load should be applied? Five by
5 E minus 3
what? 5 e raised to minus 3, yes.
megapascal. It's a stress.
Mhm. Yes, that is the pressure.
It's-
If we have to convert pressure to live load, what should we should multiply it by 25, right?
Yes.
0.125.
0 point
125. Just
negative
multiply the width. 25.
yes, like this. Okay, go to mesh. uh, Mesh element type like this. Beam, it's already selected. It's fine. Seed. I'll select here 6.25. Here also you will find convergence things 6.25, but you should do it. Okay. Then I'll create a job beam mesh. What? Submit. Tangent vectors, right? This is fine. Yes. So I think it's done now. Four point 803, right? This is. Now you may be wondering what I did here assigning this beam orientation, right? So this means actually, right? Let us do it again. It should not be done, but yes. So it's enter an approximate n1 direction. So this is how tangent vectors are shown. Like this is the you have beam section, right? When you calculate maybe PLQ by 3EI, that I is for a section, right? So the direction tangent to the section is this, and the section looks like this. 1 and 2. X-axis is like this. Second axis or maybe y-axis is like this. Okay, and I have created my load is along 2. Suppose I put my load along 1, then I should flip this. Rather not. No, I should not flip this. No, do nothing. That will also be fine. Nothing. Do nothing to it. Okay. So this is the tangent direction, and this is your 1 and 2 is section. This is square. It can be rectangular. It will compute EI. The second moment of area will be computed along this and this direction. For that, I have given. Where is that profile? I have given a rectangular profile. See, this was 1. This was 2. Okay. So it gave, and the accuracy is something like this. So do you have any questions till now? Beam element is more accurate than the solid element, but accurate when compared to analytical solution. Analytical solution is 4.8. Okay.
Yeah, I got exactly 4.8.
Yes, so that is the analytical solution. And beam element is 4.803. What was the solid element? Does anyone remember? 4.872. Not very much difference, but beam element is better, right? 0.07 millimeter. So small difference, but beam millimeter is better. Obviously, this has a huge. It has Okay, let's discuss that later. Now, does anyone have any questions till now?
No.
Create another one then. shell element. So in this one small project, you learn about, obviously you know already about solid. You now learn about shell. How to create a shell? Keep it 2D. Use shell here. Okay, that's it. Okay, now I have to create the mm, shell. So how will I create the shell? See, shell will be in this plane, something like this. Okay. Yes. So 2000 cross 25. Shell will be something like this in this plane. In XZ plane, right? XZ plane. So shell will be 0, comma 0, 2000, comma 25. Okay, like this. Done. Then again we go for property. Create the similar thing. Okay. Then you go with elasticity 2E5.3. Okay, that's it. Then you go section shell homogeneous. So it says what is the value of the shell thickness? What is the value of the shell thickness? 50, right? And I am modeling this middle fiber. So 50 millimeter. Okay. So that is one. Just leave everything as it is. Okay. Then assign it to this section definition. It's middle surface. Okay. That's it. Following that assembly, call it here. Then go to step, define one static general. Just do nothing. Field output. It is fine. Whatever it is. Okay. Following that interaction. Okay. So it is something like this. I maybe I should try to flip this, rotate this. Okay. Uh, okay. So let's rotate it. Why? Because I want to apply force in y direction. So let's rotate it. How? Instance, rotate instance. I'm not sure if I have shown you rotating instance or not. Have I shown you before? Translating we have done, but not rotating, right? So instance, select rotate and select this instance. Then it will ask you to select a point. I want it to rotate about this line, right? This line. So if it will rotate about this line, see angle of rotation 90, it will be like this. Okay. Suppose I make it rotate about this line, so then it will be like this along this direction. So it has now rotated. Go to load. Firstly, boundary condition. In initial step, you can select this or then this, whatever you want. Select this edge. Okay. And this. Okay, fixed. Then you go for pressure again. You apply pressure. Sorry. Then it says which surface, brown or purple. This is purple, this is brown. So we'll go for how much? 5 E minus 3 megapascal. Okay. So this is how it is. Then you go to mesh, you go to part, you seed it 6.25. Okay. Then you go to element type, you select this, you go like this, and you select here shell SR4. Seed it. Okay. Now I'll create another job. shell mesh 6 underscore textbox. Okay. See, actually, which is realistic solution do you think? It is beam, shell, or solid? Realistic.
I think it's beam.
It's solid. Realistic is solid. When you compare with analytical, then beam is better. Let's see what this has to offer. It gives you 4.8. Wow. It gave you 4.8. So beam and shell are more close to analytical solution than solid. Okay. Because solid is more realistic, and here you are comparing with analytical solution. One thing is there. Secondly, I want to see something. See, this is solid mesh 6.25. How much time did it take? Where will I get this? See, this is beam, then I go to shell. Okay. Here's a comparison between solid, shell, and beam. So solid is obviously most expensive, right? Followed by shell, and beam is least expensive. Okay, this is first point. Second point is accuracy is much better for beam and shell as compared to solid when we compare with analytical solution, because in analytical solution though there are certain assumptions. Okay, and if you use beam or shell elements, those assumptions are also considered by Abaqus. But realistically, solid elements have a more realistic solution. If you have elastic material, you model it like this, then solid element will give you realistic solution. Okay. Yes. Now what you can do is, now the issue is when can we use shell elements, and when can we use beam elements? Can use, or maybe one should we here we could use shell, we could use beam. So but when can we use shell elements? Can anyone say? Okay, so if one of the dimensions, or suppose this is 50, right? If this dimension 50 is much smaller than 2000, right? So if one dimension is very small as compared to the largest dimension, then you can use shell elements. Okay. Another thing is, suppose I use CDP here. Okay, then should I use beam, solid, or shell? Which one? Which one will give better? Can you rank, like this will be most accurate, or better results will be given by this element, followed by this, followed by this? Anyone? In that case, solid element will give you better result, followed by shell, and beam will give the least accurate result. Why? Because, okay, so obviously if it is you are loading in elastic regime, then it's fine. The result will be similar to what we have got. But when you go to plasticity, the beam element, it has the assumption that the material is elastic. d2y by dx2 equals to m by ei is derived from the assumption that material is elastic. So if you have non-linearity, then it's better to go with solid or shell. Beam is least preferred there. Okay. So I think I should have discussed this initially before going to CDP, so that this project is better suited at the initial. But again, you didn't know how to model with shell and uh, beam elements, so this is beneficial. Any questions? Anything?
No.
Okay. So today it was 19th or 20th or what?
19th maybe.
Okay. Yes. So I'll maybe okay, I'll show you one more thing, but let's discuss that tomorrow. We'll do one more project. That will be relatively uh, what we call relatively complex. We're using shell elements, but plane stress elements. Do you know what is plane stress problem? Plane stress condition? Anyone?
Stress in flat plate.
Oh, that is not a good definition. That is okay theoretically, but I wanted to show you, tell you what does it mean. See, so you have this stress tensor sigma 1 1, sigma 2 2, sigma 3 3, right? Normal stresses, and these are shear stresses. Okay. So in plane stress condition, your stress tensor reduces to 2 by 2. Sigma 1 1, sigma 2 2, and other all the components are 0. So this is your plane stress condition. Okay. So just, yeah, that's it. Don't go for plane strain. We'll just use plane stress. Plane stress element. Model up. I'll study size effect in beam using plane stress elements. So why do we use that? Why don't we use solid elements? Because solid elements will have huge computational cost. Like we had axis symmetric elements for columns to save our computational cost for circular columns. We can also use plane stress elements for beams to save our computational cost. And yes, that should be interesting. Okay, you should check for mesh convergence study. Okay. So I'll upload this also. If you want, you can save it for if you ever want to model with shell or beam element. Truss elements we have already discussed. Now when we model, sorry, when we modeled RC, yes, here it is. You can also try with explicit, okay? But the analysis should be quasi-static, but it that won't be. See, that won't be computationally efficient here. Can you tell me why standard is more efficient than explicit in this particular case? Anyone? Hadi, Munirul, you were only there. So standard is more efficient because we don't have any material non-linearity, right? In this case, even if we had material non-linearity, say our loading is very small, so displacement is very small. So when displacement is very small, you don't have much material non-linearity, and then you won't face any convergence issue. So there won't be any cutbacks. So standard will give you solution very fast. So you can try, see for example this mesh size, solid mesh 25, right? See your CPU time and then go with explicit. You will see explicit will have much larger time. But see it in fact it just finished the job in one increment because there was no material non-linearity. It was a linear material. Okay. Any questions? Okay, no questions. So I'll end the meeting and tomorrow we'll meet again, probably for another project. Okay. So bye.
Okay,
Bye.
bye.